Good afternoon. Since my voice is still somewhat shaky, I decided I should probably record the lecture since you'll probably be able to hear me better if I do that. Today we're covering Chapter 22, Magnetism, and Ampere's Law. First question is, what is magnetism? Well, electric charge, like with electrons and protons or electrons and quarks, comes in what are called monopoles. That means you can have a single unit of charge and the electric field then will all point to or away from that unit of charge. That's not the case with magnetic fields. There is no such thing as a magnetic monopole. And if you're a fan of the sci-fi from the 50s and 60s and maybe even the 40s, you'll read occasionally about magnetic monopoles and the magic they're supposed to have. So all magnetic fields arrive from moving electric charges, or from you moving relative to an electric charge, or from the spin of an electric charge. By spin of an electric charge, we don't necessarily mean the charge spinning, because when it comes to electrons and other fundamental particles, they all have a property called spin that gives rise to their magnetism, but it is not exactly the same as a charge spinning. So, in fact, if you were to take an electron and you were to measure the magnetic field that comes from its spin, it's actually twice as large as you would expect if it were an actual physical electric charge spinning. The question then is, what is magnetism? Or a question is, what is magnetism? And back to the previous slide. When we talk about there being no magnetic monopoles, what does that mean, or what is a consequence of that? Well, one of the consequences is that instead of like with an electric charge, you have an electric charge and you have these fields going all over the place like that. You can't have that with magnets. There has to be a north and a south pole, and the field goes from north to south, right? And actually inside the material itself. So that is a very important distinction, that you actually have to have two poles when you create a magnet. So what are magnetic materials? Magnetic materials are materials that are naturally magnetic. So the most common, or we often call this ferromagnetic, and we call this ferromagnetic because the most common magnetic material is actually iron. Iron is magnetic, or can be made into a magnet relatively easily, because iron has several unpaired d shell electrons. What does this mean? So if you look at the paired electrons create a magnetic field that looks like this, and a magnetic field that looks like this, and essentially they give rise to no net magnetism. But in the d shell of iron, you have these four unpaired electrons that give rise to a magnetic field. When iron is made, or when you take a chunk of iron, these individual atoms exert forces on each other. And that force they exert on each other causes them to try and line up with each other so that they have north pole and south poles lined up and get into a lower energy state. Now, as I mentioned before, the spin of the electron gives rise to a magnetic field that's twice what you would expect. And there was a big experiment at Brookhaven Labs that's probably about the size of our lecture hall, maybe twice the size of our lecture hall, called the G-2 experiment, that was setting out to measure this factor of 2 very precisely. Since I was at Brookhaven Labs, they've actually moved that whole thing to Fermilab. But it was so big, and one piece that was so big, they actually had to stick it onto a barge, take it down the East Coast into the Gulf of Mexico, and then they had to take it up the Mississippi River to get it to Chicago. So when we talk about ferromagnetic materials that naturally organize themselves, part of that is that they fall into little subdomains. So you'll have a couple of atoms that line up, and that creates a larger magnetic field and gets a few others to line up. So you start getting magnetic fields from individual atoms lining up. And this happens over some size volume of material. When we apply an external magnetic field, then more of them line up. And as you do this, you gradually get to the point where you have a magnet, where you actually have something that's much more uniform, like this. As you can imagine, since these already want to line up at some extent, if you heat them, you let them move freely and you give them an opportunity to line up. However, there's a temperature called the Curie temperature that if you heat them past that, then they have so much kinetic energy that the magnetic forces no longer matter. They no longer magnetize at all. For some materials, the Curie temperature is below room temperature. There are other materials called rare earth magnets that you can use to make magnets that are extremely, extremely strong. You can get up to 10 Tesla or 15 Tesla with a rare earth magnet. So it's a permanent magnet sitting there at that high a field. Now, magnetic fields exert a force on moving charges that is at right angle to the direction of motion. So we write this as the force from the magnetic field is the charge times its velocity crossed with the B field. So as I think of it as my fingers going in the direction of velocity and the magnetic field being out of my palm, and then my thumb points in the direction of the force. So I think of it always with the right hand rule like this: V cross B, or V cross B. That's just V cross B, right? That's my way of thinking about it, which is a little different from the illustration. If an electric field is also present, then the total force on the charged particle is just the charge times the E field plus the charge times its velocity crossed with the B field. Now, B field, magnetic field, those are the same things. So magnetic fields, if you have a current carrying wire in a magnetic field, the magnetic field will actually exert a force on the current in the wire. This is called the Hall effect. So let's take the current density J, which is the number of electrons per unit volume, right? The number of electrons per unit volume times the charge on an electron times the drift velocity. Remember, we had the drift velocity from a few weeks ago. So for a magnetic field perpendicular to the current, the force per unit charge, on each charge, right? Force on each charge is the charge times the drift velocity times the magnetic field times the sine of the angle between them, because it is a cross product, right? And so if the magnetic field is perpendicular to the wire, as shown here, and we got EVDB, or JB over N. The total force on the wire then has to look at what is the total charge in a given length of wire. Well, the total charge in a given length of wire is a charge density times the cross section times the length. So total charge being moved through that section of wire times the force per unit charge gives us our force on the wire, and that's ILB. In the end, we write this as the force is the current times the length of the wire crossed with the B field. Now let's consider a current running through a loop in a constant magnetic field. The loop is attached to a pivot point as shown here. So on the top of the loop and on the bottom of the loop, the current here and the angle between the B field means that the force between the current in this direction, right, B field in that direction. That means the force here is vertical. Because you got I cross B gives us a vertical force. And if we look down here, the current is in this direction. The B field is in that direction. I cross B gives us a vertical force downward. These two forces cancel out. If we look at the sides, however, we have a different story. So here we have the current coming down. We have the B field in this direction. And that means the force is coming out of us, coming out of the page at us, or out of the screen at us. Here we have the current in this direction. We have the B field this direction. That means the force here is going into the screen away from us. I can't draw that very well, but I'll try, right? So into the screen, out of the screen, which translate to what you see going on below in the figure below. Remember, torque is the distance of the lever arm, right? R cross with the force are basically RF sine theta, right? RF sine theta. So the torque on one side is W over 2 times this force, which is the same for the top, or for the current coming in and current coming out of the page, going into the page and out of the page. So this is the view from the top. The torque is W over 2 F sine theta, which is also equal to the torque from the other side. So the total torque is WF sine theta. Now, since the force is IL cross B, right, then what we have is IWLB sine theta. Well, W times L is just the area, right? That's just the area. So the torque on this current loop is the current in the loop times the area times the B field times the angle between the loop and the B field. Now, consider something. What happens when this gets to this point? All right? And you flip it so that you've got this, right? Well, this, if left alone, doesn't keep rotating. Why? Because by the time you come over here, when you come over here, well, this force doesn't make it keep going in the direction it was going, right? So what is going to happen? Let me back up just a little bit. What's going to happen with this? It's going to rotate this way, right? It's going to rotate this way. Because of the way the forces are on it, it's going to rotate this way. So eventually, it'll hit a point where you're like this, where you've got the current coming out at the top, and you've got the current going in at the bottom. Well, the forces don't flip, right? The force would still be that way. The force down here would still be that way. So this would tend to make it go back the direction it came from. Not a terribly useful machine, you might say. We'll get there in just a second. Here's what we do. This is fundamentally how we make a motor. So you've got a current loop in a magnetic field. It rotates. When you get to the crossover point, you use brushes like you see here to change the direction of the current. And you change the direction of the current so that when you reach the crossover point, you're back to that current is going into the page, and this current is coming out of the page. So that current and that current end up reversing directions every time you get to the center point. This keeps it moving, and this makes it a motor. Now, if we add more windings to our current loop, then we increase the torque. So if you add n windings, the total torque becomes I n a b cross sine theta. All right? All right. Now, Ampere's law states that if you integrate the magnetic field along a closed loop, the result is mu naught I. So if you imagine, an integration is just saying I'm adding up the magnetic field times the length of the loop around the loop. So if you imagine here, by the right-hand rule, you've got a magnetic field that goes around the current I, right? You've got this magnetic field, and if you go all the way around this thing, well, if you stay out at a given radius, the magnetic field is the same the whole way. And so the magnetic field times the distance you go is 2 pi r, b 2 pi r, which means the B field is b 2 pi r equals mu naught I, or b equals mu naught over 2 pi I over r. And the direction is given by the direction of I cross r. So mu naught in all of this, permeability of free space. Essentially a measure of how well does a magnetic field penetrate free space. Now if we look at a current loop, all right, and we ask, what is the B field at the center of a current loop? And we really do mean at the center, because it's not uniform over a current loop, right? You can see here, over here, that it loops through in different ways. Well, right down the center, though, the B field is mu naught I over 2r, where r is the radius of the loop. This we get from a law that preceded Ampere's law, the Biot-Savart law, which sums up the contributions of tiny little segments of current. Now we look at the B field in a solenoid. So a solenoid is simply a large number of windings, right? And these are windings just go on and on and on. We've got some examples in the classroom. Well, if a solenoid is long enough, and you're talking about a region of space near the center of the solenoid, then the B field is relatively constant over that distance. All right? B field's relatively constant over that distance. And the B field is equal to mu naught n, where n is the number of windings times the current. If you actually want to make this even better, you can stick an iron end cap. You can stick an iron end cap on this, and that will make the magnetic field even more uniform throughout the solenoid. When I was on the L3 experiment at CERN, we had a solenoid that most of the experiment sat inside of it. Now, this solenoid ran, what did it run? 30,000 amps at 120 volts, and it had a field strength in the middle that was 0.5 Tesla over a volume roughly the size of our classroom. So it's a very large magnetic field with a fairly high strength, especially for that volume. Now before we talked about magnetic field creates a force on a current carrying wire. So what happens if you have two wires? All right, if you have two wires, well, magnetic field at I2 in this picture, magnetic field at I2 due to I1, we would call B1 equals mu naught I1 over 2 pi r. This is just the B field due to a line of charge. And the total B field due to these two lines of charges is the B field, is the sum of the B fields from the two of them. So the force on wire 2 then is I2LB1, where because of the way we have them parallel to each other here, sine theta is 1. So the force on wire 2 is mu naught times the length of the wire divided by 2 pi r times I2 times I1. Well, the forces on these wires are equal and opposite to each other. So F2 is minus F1, we'll just call it F, and we'll look at it in terms of force per unit length, since the length of the wires isn't something we really know. The force per unit length, F over L, is mu naught I1, I2 over 2 pi r, where r is the distance between them. All right, and that takes us to the end of this lecture. Hopefully this works. I'm going to post it. We will see how it goes, and I'll also write up some examples of problems, and